This is a tutorial to develop a discrete event simulation for the factory system we discussed in class using a process interaction worldview. The factory system was described as following. In the factory, there's a large number of machines. In this case, there's 50 machines that work constantly throughout a 8-hour workday and 5-day work week. Each of these machines operates until it fails. So it fails after some random duration, which in this case is modeled with a uniform process generator between 132 hours and 182 hours. When a machine fails, it's immediately replaced with one of the spares that are on hand, and a repairer is called in to fix the failed machine. The repairer works for between 4 and 10 hours to repair the machine, and once repaired, it gets returned into the spares pool. The overall objective of this problem is to minimize the total cost of operating the factory, including the cost of hiring all of the workers and the cost of acquiring some number of spare machines. The other issue is that if a machine fails and there's no spare that's immediately available, there's an opportunity cost of $20 per hour per machine to count loss of productivity. In lecture, we modeled this system using a combination of 3 different processes. There's one overarching process that we call run, which launches the 50 machine processes and also captures the daily operating costs of having some number of spare machines and some number of repairers. Each of these 50 machines has its own process where it essentially waits for some duration and then generates a repair process. Meanwhile, it requests a spare part and incurs any cost associated with delays in acquiring that spare part. The third process, the repair process, requests one of the repairers, waits a period of time to perform the repair, then releases the spare back to the spares pool and releases the repairer back to the repair pool. Now in this example, I'm going to use a process-oriented coding style to represent the simulation. However, you could also use an object-oriented coding style, and that would reduce the need to use global variables to transfer information across different functions. So the first thing I'm going to do is start by creating I'm going to import the required packages. I'm going to import the SIMPy package and import the numpy package and refer to it as np. I'm going to then set up my SIMPy environment. I'm going to first set the random number seed. We'll use the number 0 in this case. Create the SIMPy environment. And then run the environment for some period of time. Let's say just to start debugging some of the activities for 8 hours and 5 days. So for 40 total hours. Now we can start by defining our top level process, this run process. Let's call it factory run. And this process is going to need to know first of all, the SIMPy environment that we're going to be using. This overall problem is going to require 2 types of shared resources. The first type of shared resource are the repairers. These are kind of like servers in a queuing model. They're individual people who get requested by within the repair process and then released after the repair is completed. I'm going to create a shared resource down in my kind of simulation script. So I'll create a variable called repairers and assign this to be a SIMPy resource in our SIMPy environment and with a starting capacity of some number of workers. Let's say, for example, that we'll start thinking about having 3 repairers on staff. The other shared resource that we need are the spares. The spares are treated a little bit differently than just a shared resource because they form kind of a shared pool of resources. In SIMPy, we can represent this with a separate idea called a container. So we'll create a variable for the spares and assign to that variable a SIMPy container. This is in the same SIMPy environment. We can say that initially there are 20 spares, and then our total capacity for spares is also 20. By representing the spares as a container rather than a resource, it allows us some new methods to request and release individual components from it. All right, so let's continue working on our factory method, our factory run process. We'll need to pass in as arguments the repairers and the spares so that this process can modify and use these variables. The other thing, as we're adding in those arguments, let's also, in our SIMPy environment, add in a new process, and we'll launch the factory run process with the environment, the repairers, and the spares. Okay, so now that we have our factory environment, we can start writing in some of these activities in the activity diagram. So the first thing that a factory will have to deal with is uh, launching the 50 machine processes, and then also keeping track of the recurring costs. So let's create a variable to store those costs. This is kind of like a state variable again, similar to the other applications that we've been looking at. Again, since we're using a process-based coding style, we'll need to define this as a global variable because some of the other processes are going to require to modify and update this variable for cost. Right, so then while we've defined a state variable to keep track of our costs, we can launch our 50 operate machine activities. So for each of a temporary variable I in the range of 50, we will want to, with the SIMPy environment, launch a new process, and it will be the operate machine process, which we'll define just below. This one will also need these three arguments: the SIMPy environment, the resource of repairers, and then the container of spares. So let's just define a placeholder for this right now. Define a new function for operate machine with these three arguments, and we'll just have this. I'll just leave this blank for this moment. So when the factory run generator starts, it launches all 50 of these machine tasks. It's not yielding for wait for each of these to finish. It's just launching these processes and moving on. The other thing that it has to manage is this recurring loop of managing the costs. So this will be there'll be a while true loop. So this kind of tabulation will happen continuously throughout the simulation. And what we need to do each time is to update the cost and add to it 375 times 8 hours times the number of repairers. So the number of repairers is simply the capacity of this SIMPy resource. They're working for 8 hours a day and for 375 an hour. Then we also have to add in the cost of the spares. It costs $30 a day for each of the spares that we purchase initially. So 30 times spares.capacity. For this, we'll want this to repeat every 8 hours. So we're going to yield for a timeout of 8 hours. So this cost will be appended every 8 hours, and it will continue in this loop. Okay, so next is to define the operate machine process. This is going to follow this larger block in the activity diagram. The first thing we'll need to do is to wait for a certain duration. This is similar to an inter-arrival period, but this is the period waiting for the machine to break. And then we'll launch a repair process and meanwhile request a spare and add in any costs that are incurred while waiting for that spare. So the first thing I'm going to do is to declare the global cost variable, because we're going to need to modify that later on. Each machine is represented as entering a infinite loop. So while that machine is, you can think of this as the machine location and not the specific machine, which is swapped out for a spare. But the first thing this will do is wait for an inter-arrival period, or the period for it to break. I'm just going to put this into a separate function. I'll create a separate process generator for this. Define a, let's call this a time to failure. This is our process generator. It follows a uniform distribution between 132 and 182 hours. So the time to failure, I'm going to return a numpy.random.uniform between 132 and 182. So in our operate machine process, we're going to yield for a timeout period of the time to failure. And at this point, then we know that the machine has been broken, so we can just store this in a temporary variable. T broken is the current environment time. We'll need to launch the repair process. So I'm just going to put a comment in here right now, launch repair process. And then after that repair process finishes, we will note the time that this machine has been replaced. Well, first we need to get a spare. So we're going to yield until the spares allow us to get one. So this is the notation to allow us to wait until one spare becomes available. So it's similar to the requests for other resources in SIMPy. So after we get a spare, we can log what time this machine was replaced at. Just also put in some comments to help us debug. Print machine broke. So just putting a message here to print the time at which a machine broke, and also put the time that it was replaced. And just to make it look a little bit better, I'll format these as a floating point number with 2 decimal places using the format notation : period, or : 0.2f. All right, so the machines, while they're operating, they can wait for a timeout until they break. They log what time they broke at. They print out a message. They wait until a spares becomes available. They log what time they were replaced. Then we need to add up the cost of how long it costs to be down for. So the cost gets added to it. $20 is the penalty for being out of service. 20 times the amount of time it was down, so T replaced minus T broken. And that finishes the operate machine process. So let's take a look at what this looks like so far. This is not quite finished yet because we didn't finish this repair process, but it will give us some initial information. And we'll see, actually, we don't get any outputs because our simulation is only running for 40 hours, and 40 hours isn't long enough for any of these failures to actually take place. So let's expand this from 40 hours for one work week to a full working year, 52 weeks. So with that small change into the simulation parameters, we can see now that there's lots of information about what time a machine broke, and then what time it was replaced. And we see after a certain period of time, I think it's after our 20 spares have been used up, none of the other machines actually get replaced. So let's finish the last process here. We'll create a repair process. So let's just create another generator, define repair machine. This one is also going to require these 3 arguments: the SIMPy environment, the repairs resource, and the spares container. This repair process is going to be working in this last period, this last block in the activity diagram. The first thing we want to do is request one of the repairs. So with repairs dot request as request, then yield for that request to be complete. So once we have a repair, then we can perform the repair process or perform the repair activity. This is going to require another process generator. We need to define a repair time, generate repair time function. This one is also going to use a uniform distribution between 4 and 10 hours to complete the repair. And just for consistency, let's also use the generate keyword here for this function. So generate time to failure and generate repair time. Okay, so back in the repair machine process, we've waited for the repair to become available. Now we can yield for a certain timeout period to generate the repair time. And then after that repair has been completed, we can put the spare back in the spare pool. So the notation for this in SIMPy is to use the function put. So similar to how we yielded to get one of the spares out of the spares pool, this allows us to wait until we can put a spare back in the spare pool. In this case, we know that we're never really going to have to wait for this because we know that we have enough capacity for our spares. We start with 20 and we only have capacity for 20. However, if there were a slightly different scenario with a smaller capacity of a spares pool, we may have to wait for a space to actually become available. So that's pretty much it for the repair activity. We've waited for the repair to become available. We've waited some period of time for the repair to take place, and then we've put the spare back in the spare pool. So let's just add in a debug message here. So I'm going to indent it outside of the with statement. So this will happen after the repair is released. We're going to have a message saying repair complete at the current time. Last thing is just to add this into our placeholder, into our operate machine activity. Here, we don't have to wait for the repair to finish. We just have to launch the repair process. So we're gonna, using the SIMPy environment, process the repair repair machine process, and pass in the environment, the repairs, and the spares as arguments. All right, let's take a look at the results here. Now we're seeing, at least in the initial log messages, it's looking more promising. We're having series throughout this long simulation of machines breaking, being replaced, and repairs becoming complete. So let's just add in one more, we'll add in a process monitor so we can generate some data for some plots. So some of the information that we might be interested in are maybe take observation times. So we'll create a new list for this. Let's look at the cost that we've incurred at different times. And let's also look at the number of spares that we have available at different times. So with these three data are what we're going to log or what we're going to observe. Define another process to observe the simulation. It needs the SIMPy environment and any resources that we want to observe. So maybe the spares resources one that we'll want to log. This one is going to be a continuous process. So while true, we want to log the observed time. So append to this data the current environment time. So environment.now. The observed cost will append the cost state variable that we have been using before, this global cost. Again, we should be careful about using these global variables. We don't need to declare them as global variables if we're not changing their value, but this is easily broken in a larger simulation model because you may accidentally define more than one variable with the name cost. But for this small case, it's okay. The last observation, let's take the observed number of spares and append in the spares dot level. So for For containers, there is a special variable called level, which lets us know how many spares are available at this particular time. And let's just fix our variables here: observed time, observed cost, observed spares. And this process monitor will happen, let's say, every 1 hour. So we'll yield a timeout period of 1 hour between the logging of these three data. So we then have to add in this observation process to the SIMPy environment. So we'll add a new process to observe this environment and the spares. And if we run the simulation, looks like I have a typo here. I'll append to the spares, rerun the simulation, take a look at the observed time, get a nice list of every hour, the observed spares. We also have a nice list. And then we can start to build some plots to show this information over time. So let's import matplotlib.pyplot as PLT, make a figure, and plot using let's use a step chart. X-axis will be the observed time. Y-axis is the observed spares. Let's just add some labels in here. X label is time in hours. The Y label is spares, so number of spares, or spares level. All right, take a look at this. So we can see kind of an oscillating behavior between 20 and looks about 10 spares. This indicates that maybe we have too many spares available in our system. So let's also create another plot of the cost that's incurred. This one keep as a step plot. Oop, forgot to add in the where equals post. This will be just a small difference in this visualization. So now I'm plotting both the spares level and observed cost and the observed cost throughout the simulation. Looks like this is actually an interesting behavior that at the beginning of the simulation, there's a big jump in cost, and it corresponds actually right to this period of time where we have no spares available. This is an interesting implication of starting all of the machine processes at the same time. So this, the failure mode is a uniform, the failure duration is a uniform distribution, which does not have the memoryless property that exponential distributions do. So by starting all of these machines at the exact same time at time 0, we're kind of we're implying a correlation in their first failure time. The first failure will, for all 50 machines, will happen between 132 and 182 hours into the simulation. And what this actually means is that it will completely exhaust our spares, and it will slowly replenish the machines as those spares become available. And in a longer term, it looks the failure time of these 50 machines gets more distributed over time. So these plots, if I'm looking at them, it appears that maybe we can reduce our number of spares. So maybe from 20, we can drop it down to 15. And maybe that will reduce our overall cost. So I'll just print out here. Our final cost is the observed cost in the array element -1. So it says total cost was blank, and format this cost data, and I'll print it as a 2 decimal point floating point number. So :.2f means format this number as a floating point with 2 decimal places. So it looks like if we drop down to 15 spares, total cost was about 150,000. If we go back to our original design point of 20 spares, we had 180,000. So there was an improvement